The other stack processor is stripmapStack. The important thing here is TopStack. Currently, there's only one publicly available TOPS mode dataset, which is Sentinel-1. So it's easier to control everything from data to later stages. StripMap, there's a lot of sensors, so there's a little more work up front to generate these stacks. However, the stripmapStack processor is a more generalized workflow. It can handle data in native Doppler or zero Doppler. You can start from raw data, or you can start from SLCs. The most important change has to do with L-band data, which I don't think there's another stack processor in the public domain that includes the ionosphere correction and the rubber sheeting of SLCs as part of the stack generation. So the way the complete stripmapStack workflow works is shown on the right from another paper by Harish. So we start with computing the offsets. Then we use first a coarse stack of SLCs purely using geometry. Then we use amplitude cross correlation. And in TopStack, if you remember, we use a constant offset in range and in azimuth. But stripmapStack has the ability to estimate a pixel offset time series for blocks of data and use that for generating the co-registered SLCs. The reason being ionosphere can be large enough that can move pixels around in azimuth. So you essentially need a time series of offsets before you're able to align SLCs precisely at full resolution. You can, of course, turn off all that and go back to the standard mode. The default is to just do constant offset in range and azimuth. But you can turn on ionosphere and get the whole workflow of pixel offsets and then co-registered SLCs. Here's an example of application of this stack processor over data from Chile. Harish knows this data set more. You should probably talk to it than me.
Well, you can talk to it, Piyush. Go ahead, please.
So I think this demonstrates the need for pixel offset time series before doing the co-registration for L-band. For example, you see these big, huge fringes in this area in Chile, in South America. It's close to the southern anomaly, magnetic anomaly. And a lot of the signal is essentially ionosphere. And the ionosphere is large enough that you can see this scale goes from +1 pixel to -2 pixel. And in fact, it saturates here. So ionosphere effects can be strong enough at L-band that they can move pixels around by more than a pixel, which leads to complete decorrelation when you're trying to do interferometry with it. As a result, you first estimate the time series of pixel offsets, then use that along with the geometry to generate the co-registered SLCs. And in the process, once you have the full offset transformation, you also split the band into high band and low band, estimate the ionosphere, and this is essentially the estimated ionosphere by range split spectrum method. You can see the original interferogram and the estimated ionosphere. And this is the corrected interferogram post the ionosphere correction. I believe this pair is where the earthquake occurs. But as you can see, there is a little bit of leakage into dates before and after, but this is way better than you see all these interferograms impacted by ionosphere. And you can also see that there are certain dates when the ionosphere is active and certain dates when the ionosphere isn't. So there's no way of knowing a priori what could be happening, at least as of now. Maybe we'll come up with methods in the future. So for L-band stack processing, you would typically see decorrelated streaks in your data. If you see that, we recommend you turn on the pixel offset rubber sheeting while doing the L-band stack generation. Anything to add, Harish?
No, Piyush, thank you. It's complete.
There's another thing I'd like to point out, which I think Harish also emphasized. So these are fairly long images. So these are probably 300, 400 kilometer long images. And most ALOS frames are small. So if you were to plot an ALOS frame here, this would look like a ramp. So essentially, the ionosphere is a much spatially longer wavelength feature. And this method, the split spectrum method, works great for the long wavelength. And for the scintillations, we still have to rely on rubber sheeting to account for it. The workflow setup is very similar to StopStack. I don't think we're going to do an example, but you've seen how Stack Sentinel works. That's how Stack stripmap also works essentially. You have to do, like I said, a little bit more work up front. You have to download the data, and you have to run the unpack frame sensor on each input data and create one folder per date yourself. That's because the data could be raw, it could be SLC. There's just too many variants for us to capture in a simple script. And once you've organized your data, you set up your DEM again, and then you run Stack stripmap. The options are very similar. Same, you have an option of doing bounding box, in which case it can crop the data as well. Then here you get to specify the temporal base. There in TopStack, you saw the number of connections as the way of specifying the pairs you want to process. Here, you specify the pairs you want to process using a temporal baseline threshold in days and a perpendicular baseline threshold in meters. But otherwise, the approach is pretty much the same. There are a few more flags you may have to pay attention to. This comes from being aware of what data is your input. Suppose you're starting with Sentinel-1 stripmap SLCs, like they have over certain volcanoes. You want to explicitly say 0 because the SLCs are in 0 Doppler, and you want to add a no focus flag because the data has already been focused, so it will skip focusing the data. If you're starting from raw data, the default ICE SLC processor focuses it to native Doppler. So you should not specify 0 in that case. So you just need to know what your data sets are like. For TerraSAR-X, Cosmos SkyMed, most pre-focused SLCs, you want to specify 0 on no focus. ALOS 1 is an exception. ALOS 1 SLCs were native Doppler, so you just specify no focus. You will get familiar with once you read up more on the data set that you're gathering to process into a stack. And similar options, number of looks, filter strength, unwrap method, get to control the reference state. And the workflows here include SLC, interprogram, and ionosphere options. What does Stack stripmap create? Again, it's very similar. It creates run files, it creates config files, and one config file is one command, and one file is just a collection of config files. I also want to point out that the Stack processor, since a lot of the improvements and developments have come from the University of Miami group, it's really well integrated with MintPy. So you should be able to read the outputs of the Stack processor workflows into MintPy. I would also say read the MintPy documentation. They have some very nice examples on how to do this. I also know David maintains a prep stack to stamps package. This is also available within the ICE repository itself. It essentially takes the output of the Stack processors and pre-processes and repackages it so that stamps can work with this data. So I don't know if there are other tools. There may be other tools out there that readily work with Stack processor outputs, but I think a fairly large number of advanced users are working with the Stack processor and MintPy. That's all. Yep, go ahead.
There is a question on the chat. I think we missed. Does the 2010 date corrected InSAR for tropospheric phase? I assume that refers to the slide that you had all the interprograms?
This one?
Is that the question, Jessica? I'm not sure. There are too many 2010. Which one?
Yes, that's the question.
So yeah, the first row, as Piyush said, actually, these are the result of a time series. We had networks of small baseline interferograms, and since it was LOS1, then we had to actually constrain the both perpendicular and the temporal baselines. So we did the time series, and on the top, you see the differential time series. So already the correlation noise has been beat down a lot. And then the estimated ionosphere, and then third row, as Piyush said, is what is corrected for ionosphere, but yeah, troposphere is still there. The second interprogram shows the nice coseismic displacement signal. So all those fringes in the between 2007 September and 2008 January, that's coseismic displacement. And then the rest of them are dominated by atmosphere, troposphere, or residual ionosphere, high frequency ionosphere, which full spectrum cannot take care of, or 2008 March and 2008 September, that one is dominated by DM error, because the spatial baseline there is 4 kilometers almost, 3,681 meters. So the residual is very nicely correlated with the DM, and it's DM error there. So I hope that answers your question. February, March. Yeah, definitely. There is troposphere.
Yeah, so that's all I had on the stack processor. I would say read through the README files. They should have step-by-step instructions. And you'll see that these Python scripts are fairly short. They essentially read input folder names, input parameters, then they call one ICE module, they run it, and then they save the outputs. So if you are familiar with Python, these will be really easy to work with.
So once the interferograms are created from the stack processor, the MinPy, if you specify ICE in the input load line for MinPy, it just understands those formats, correct?
Yes, that's correct, Paul.
And easy.
And I believe the example data set on the MinPy web page, the repo was generated with the stack processor. Am I right, Jun, Harish?
Yes, that's correct. And the ICE is actually the default one.
Yeah.